Right now, as you watch this video, something is right in front of you that you'll never see, not because of bad eyesight or something too small or far away. No, nature itself hides this from you on purpose. What is it? Stick with me, because by the end of this journey, your whole view of reality will flip upside down forever. Why should you care? Because the way we think the world works is dead wrong. The world you see is just a shadow of its true self. Imagine your room, the walls, ceiling, the light from your screen. It feels familiar, right? But from the laws that govern reality, your room looks completely different, and honestly, it's unsettling. Your eyes see just a sliver of the electromagnetic spectrum, only about 35%. That means most radiation around you, infrared from your body, ultraviolet from lights, even Wi-Fi radio waves, passes unnoticed. You are peeking at the universe through a keyhole, missing everything else behind the door. And here's a twist: between the atoms in your body, in what seems like empty space, virtual particles burst to life and vanish instantly. This quantum foam is real, buzzing beneath your skin, yet invisible no matter how advanced our instruments get. Out there 160 billion light years away, events are happening you'll never witness. It could be a star exploding or a galaxy forming. Maybe someone there is looking at their skies, pondering similar questions. But no matter what, you'll never see that, not because of weak telescopes or short lifespans, but because the universe expands too fast for light to reach us. So here's the big question. Are there things we fundamentally can't know, no matter how hard we try? The answer: yes. There are three kinds of limits to knowledge. First, practical limits, barriers we can overcome with better tools. Second, physical limits, hard-coded by the laws of nature. And finally, cognitive limits, restrictions built into the human brain itself. Consider this: the oldest known star carving is 500 years old, found etched on a mammoth tusk. It shows Orion's constellation, stars still shining today. Imagine the ancient person carving it in the harsh ice age, with no science or writing, staring at an unreachable sky pattern. That was their boundary, practical and vast. Today, we know Orion is between 240 and 300 light years away. One star, Betelgeuse, is 700 times bigger than the Sun, and the Orion Nebula is a stellar nursery where stars are born thanks to our tools. That ancient boundary has been pushed back massively. Then there are physical boundaries, like the cosmological horizon, currently 46.5 billion light years away. As the universe expands, this horizon moves closer, shrinking the part of space and time we can observe. Objects beyond it hurtle away faster than light itself. No telescope can reach there, not because of tech, but because space stretches faster than light can chase. Or think about Heisenberg's uncertainty principle. You can precisely know a particle's position and momentum at the same time. This isn't a technical flaw, it's a fundamental rule of nature. It's like trying to say a square is round, just impossible at its core. And then there's the toughest limit, the cognitive one. Our brains evolved in harsh savannas to survive threats, find food, and reproduce. They weren't designed to understand quantum physics, relativity, or multidimensional topology. Some ideas may forever lie beyond our grasp, like an ant trying to decode a The journey begins with the triumph of human knowledge, tools breaking practical limits, then the mind-bending world of quantum physics revealing physical limits. Finally, we reach the cognitive abyss, the hardest barriers in understanding, and through it all, we ask, are we truly limitless or forever confined? Two brilliant physicists offer radically different answers. David Deutsch, a quantum computing pioneer, sees infinite possibility. No law forbids knowledge, so all solvable problems will eventually be solved. We read at the start of endless discovery. On the flip side, Brian Greene warns entropy dooms us. Thermal death will kill thought, turning the universe lifeless, making ultimate knowledge impossible. Deutsch's vision is a manifesto for optimism. Knowledge conquers all. Green's view is steeped in realism. Life and intelligence are fleeting phenomena, so who's right? Maybe both, maybe neither. Maybe the question itself isn't quite right to know. We must journey deeper into reality's fabric. We live in an extraordinary moment. The universe is young enough for us to see its past, its violent birth and starry history, but this window shrinks, and future beings may see nothing but black void with a few lonely stars. Our moment to witness cosmic history is fleeting, a privilege and a curse. Through the James Webb Space Telescope, launched in 2021, worth $10 billion, built by 20,000 engineers over 20 years. It's the most complex and risky scientific instrument ever sent to space. Unlike Hubble, it can be repaired. It's out 1.5 million km away at Lagrange point L2. One mistake could mean total mission failure. JWST is folded like origami to fit into the rocket. Every mirror segment, every shield layer, every tool needed to unfold perfectly in space. 344 critical points where failure was possible. Miraculously, every single one worked. Its massive 6.5-meter gold-coated beryllium mirror is key to sensing faint infrared light from the distant universe. Infrared light lets JWST see the earliest galaxies when the universe was just a few 100 million years old. The telescope is kept ultra-cold, colder than deep space, to avoid blinding itself with heat. It's a triumph of technology. a testament to human curiosity beyond instant profit or destruction. In 2024, JWST spotted young star ST6 in the Large Magellanic Cloud, a small galaxy 160,000 light-years away in its icy cocoon. Detected 5 complex organic molecules: methanol, ethanol, acetic acid, acetaldehyde, and methyl formate. These are the very ingredients of life found in the early universe's tough conditions. For this, only methanol was reliably found in our galaxy's protostars. Now, more complex organic chemistry appears possible across galaxies, even in environments with fewer heavy elements. This hints that life's building blocks might not be Earth's lucky accident, but a cosmic inevitability, a universal recipe unfolding across space and time. JWST also revealed the Firefly Sparkle galaxy, as it was 600 million years after the Big Bang, small and brimming with active star clusters. It defies our models of early galaxy formation. Even stranger, the supermassive black hole at its center weighs 2 million suns, impossible by current theories given the universe's young. Discoveries like Firefly Sparkle challenge our understanding. Maybe tiny primordial black holes seeded today's massive ones, or perhaps we are missing cosmic forces that speed up growth. James Webb's data is pushing us to rethink everything about the early universe, a thrilling, unsettling frontier. Even the Webb has limits. Its resolution maxes out around 1 arcsecond. Imagine trying to spot a coin from 40 km. To see finer details, you'd need a bigger mirror or shorter wavelengths. Plus, Webb only sees infrared. Other light types demand other instruments, and capturing faint targets needs hours of observation, mapping the whole sky millions of years. More limiting is the cosmological horizon itself. Beyond about 16 billion light-years, galaxies recede too fast for their light ever to reach us. No matter our tech advances, that region remains forever out of reach, a cosmic wall imposed by the geometry of spacetime. Trillions of years, when our stars dim and die, hypothetical distant civilizations might see nothing but endless darkness. No galaxies, no cosmic microwave background, just a black void. Astronomy becomes impossible. The story of the universe, once written in the stars, will vanish into silence. We live in a uniquely revealing epoch now. The universe is young enough for us to glimpse its history before the curtain closes forever. But knowledge isn't constant. It depends on when, where, and who investigates. We're lucky to peek now, yet also cursed that much remains hidden, forever out of reach. Back in 1936, Einstein showed massive objects bend space and light, acting like lenses. He thought it was unobservable, just academic curiosity. But in 1979, astronomers found a quasar appearing doubled, caused by a massive galaxy bending its light. Einstein's useless idea became a cornerstone of astronomy, helping us see farther and clearer than ever. Now humans plan to use the sun itself as a gravitational lens. At about 550 astronomical units, 82 billion km away, solar gravity focuses distant light into a single point, magnifying it 100 billion times. For perspective, Hubble magnifies 1,000,000 times, JWST about 100 million. The sun lens is 100 billion. Such magnification, we could map Earth like exoplanets hundreds of light-years away, spotting continents, oceans, weather systems, even possible signs of life. Imagine seeing a green patch that might be chlorophyll or city lights twinkling at night. It sounds sci-fi, but NASA's been working on conceptual designs, planning for 2030's mission. Patch 550 is nearly 4 times Pluto's orbit. Voyager 1, our farthest probe, took over 40 years to reach 160, traveling 3.60 per year. To reach solar lens focal point at current speeds would take over a century. Too long for us. To make this happen within decades, new tech is needed. Enter solar sails, giant mirrored sheets over 1,000 m2, pushed by sunlight's minute but steady pressure. The Breakthrough Starshot project proved this on tiny CubeSats, accelerating craft to about 20 per year. At that speed, the solar lens focal point is reachable in 25-30 years, possibly within a human lifetime. Mission won't be one big craft, but a swarm of small satellites, each the size of a fridge. Together they create a virtual lens aperture, collecting data from 1,000 different positions over months or years. This complex dance will yield an ultra-high-resolution image impossible with any single telescope. The sun complicates things. Its million-degree corona creates noise, scattering and warping the light we want also. The lens warps images into huge, elongated rings. Fortunately, we have math techniques to untangle this distortion, reconstructing the original pictures clearly. At 550, sunlight is 300,000 times weaker than Earth orbit, making solar panels useless. Instead, probes rely on radioisotope thermoelectric generators like Voyager S, powered by plutonium decay. Communications take over 60 hours one way, sending just 1 kbit per second. Painstakingly slow but worth it data stream. Imagine probes arriving decades from now, aiming at Proxima Centauri b, the nearest potentially habitable exoplanet, 4 light-years away. Months of signal collection and data relay reveal oceans, continents, atmospheric oxygen, methane, water vapor, biosignatures, seasons, maybe even signs of vegetation. First direct proof of alien life on another world. Yet the Sun's lens can only focus on one spot at a time. Want to observe another exoplanet? Another probe must be sent millions or billions of kilometers away for its own focal line. Different targets need separate, extremely costly missions. No quick retargeting like normal telescopes. Even with solar lensing, ultimate walls hold strong. The cosmological horizon restricts how far we can see. Diffraction limits set a smallest size resolvable. For solar lens, about 10 km objects on exoplanets hundreds of light years away. We 1T see individual buildings or aliens, just continents and oceans. This is the cosmic irony. We can spot possible life habitats, but miss intelligent life itself. Images update over years, too slow to observe rapid changes. Our understanding will always be incomplete. New windows open, yet reveal bigger walls beyond. Going deeper, the fabric of reality itself has puzzling limits. In the quantum world, particles exist everywhere and nowhere at once. Observation changes outcomes. Classical ideas like position and momentum lose meaning. This breakthrough battle of brilliance and bafflement reshaped science forever. In 1927, Werner Heisenberg introduced the uncertainty principle. It states we cannot simultaneously know exact position and momentum. This principle is a law, not a technical flaw. Before measurement, particles exist in superpositions, fuzzy, spread-out states. The universe is fundamentally probabilistic. For example, measuring an electron's position very precisely makes its speed wildly uncertain, maybe 580 km/s. Contrast with a 7 kg bowling ball measured to 1 millimeter. Its speed uncertainty is negligible over the universe's age. Quantum effects vanish macroscopically but dominate atoms. 2019, Vienna scientists pushed quantum weirdness further than thought possible. They sent a massive molecule, 948 atoms over 25,000 atomic units, through a quantum interferometer at 227 degrees C. It passed multiple slits at once, displaying interference patterns like single particles, shattering limits on quantum superpositions size. This means the boundary between classic and quantum worlds may not exist. Even big, complex objects might be quantum shifty if isolated enough. But because of interactions with environments, superpositions collapse quickly. Our everyday world might just be a fuzzy projection out of quantum chaos. Yet deeper limits exist. The Planck length, about 1035 meters, 100,000 billion trillion times smaller than a proton. Here, space and time themselves become fuzzy. This tiniest scale blends fundamental constants and challenges our understanding of reality's fabric. Today, fueled by the James Webb Telescope, quantum experiments, and theoretical leaps, humanity pushes toward understanding these deep cosmic and cognitive limits. We venture forth, chasing shadows, knowing we'll uncover more mysteries than answers. Our quest for truth is endless. Ancient stargazer carving Orion wondered about the sky without knowledge of stars or gravity. Thousands of years later, we know so much more, yet the universe still hides infinite secrets. The real meaning lies not in final truths, but in our endless journey, not in answers, but questions. From humble beginnings chiseling bones through monumental telescopes like James Webb, to plans for solar gravitational lenses decades away, the human thirst for knowledge shines uniquely. We are the only known species striving to explore what seems unreachable, turning dreams into reality. Faced with practical, physical, and cognitive barriers, we persist. Optimism spurs invention. Realism tempers expectations. Remember, each scientific breakthrough reveals more questions. Limitations guarantee dead ends their directions, guiding where to probe next. The universe's grand mysteries are as much about our limits as its secrets. Perhaps the greatest discovery is understanding our place in this vast, mysterious dance, a story written in stars, particles, and our searching minds. Infinite truths await us, or will some forever lie beyond reach? Maybe the questions shape us more than the answers. Share your thoughts below. What mysteries do you wish we could solve, and which should remain sacred? Our journey through knowledge's limits is just beginning. Every new beam of light, every quantum experiment, every question we ask is a step deeper into the cosmic unknown. Stay curious, because the universe never stops surprising us.